So we were talking about alternating series. What we'll do is we'll talk about alternating series. We'll do some problems in the handout. Then we'll go back and talk about the last two tests. So we talked about this yesterday. An alternating series is where you have -1 raised to a power involving n. And so the sign alternates between positive and negative. And for those kinds of series to converge, they're much more relaxed convergence criteria. So all you have to have is that the nth term of the series, the non-alternating part of the series, goes to 0 as n goes to infinity, and that the n plus first term is less than or equal to the nth term for all n. Which I always wondered about. You know, it seems like if it was just the first few n, it wouldn't make any difference. You know, if you have, as long as it went to, as long as at some point it started getting less, but that's what the rule says, so I guess I'll follow it. So we said that, you know, this series 1 over n, the summation, actually, we said this one diverges. It's a p series, and it diverges because the exponent p is less than or equal to 1. It's equal to 1, whereas the alternating series does converge. And you can also find that the remainder, the remainder is what's basically with the leftover part. You know, if you get to the nth term of the infinite series, that the difference between the final sum and the nth term sum is going to be called the remainder, and that's always less than or equal to the n plus first term. So it says if a convergent alternating series satisfies the condition that a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder involved in approximating the sum s by s sub n is less than or equal to the first neglected term. So you're always going to have, yes?
Is that how you can know that you've calculated pi or like any constant to a certain number of digits?
Yes, right. Yeah, each additional term is going to be, the error is always going to be less than that one additional term. I guess it kind of makes sense because the next, since it's alternating, the next one's going to, if it's positive, then the next one's going to be negative, and so it's always going to end up. But yeah, that's the answer. That's how, if you want to know, if you want to use an alternating series for knowing when to quit the calculation. So, you know, your calculator, I've always assumed this is the way it works, that the way the sine and the cosine and e to the x are determined on a calculator is using n terms of an infinite series. And so if you want it to be accurate to 10 digits, how many terms do you have to take? So that's what the remainder does. It bounds that error. And what is this? Oh yeah, there's two kinds of convergence. There's absolute convergence. It says if the series, the absolute value of a sub n converges, then the series also converges. Okay. So it doesn't matter what the sign of a sub n. A sub n is the non-alternating part. So I guess if this has, either whether it's plus or minus, if the absolute value of this a sub n converges, then the part that has something that's not always positive converges. Okay. I'm trying to remember what this means. Think about this. Yeah, well, I guess what it says. So there's two kinds of convergence: absolute convergence and conditional convergence. I think this shows up later when we talk about specific infinite series. As I said, a lot of them are alternating series that are useful. So conditional convergence, I think, means that it could converge, but it could diverge. There's some additional, you have to do some additional tests. So even though this thing is satisfied, if this is true, if it's a conditionally convergent series, then you can't use this test to be absolutely sure about the convergence. So you have to use another test to confirm the convergence. Whereas if it's absolutely convergent, you don't have to worry about any additional analysis. Because a lot of times you can use more than one method for determining convergence. It turns out, as we'll find out in a couple of sections, is that most of the infinite series that are useful, like sine and cosine, and you're looking to figure out what values of x those series converge for, that one test is used for convergence at everywhere except the endpoints of the interval that you're looking at. So actually, sine and cosine are good from negative infinity to positive infinity, but some of them are only good between positive and -1. And you can use the ratio test to determine the values of x that define the interval, but you have to use one of these other tests to evaluate the endpoints. So it's kind of interesting. We learned, I don't know how many convergence tests. Turns out one's the most important, and all of them are kind of subservient to that. So we haven't talked about that test yet. Okay, so let's just look at well, we've already done this one basically. So a sub n is 1 over n. So an alternating series, all of the other series, a sub n is this whole thing. But when you have an alternating series, what we have here is the summation from n equals 1 to infinity of -1 to the n plus 1 times a sub n, where a sub n is equal to 1 over n. So you got the alternating part plus the nth term of the series. And the convergence criteria for an alternating series, the two requirements are that the limit as n goes to infinity of a sub n equals 0, which it does. So if you take the limit as n goes to infinity of 1 over n, if you just plug in infinity, you'll get 1 over infinity, which is 0. So check. And the second convergence criteria is that a sub n plus 1 is always less than a sub n. I don't know if the 0 is required. Let's go back and check that out. I can't remember. No, so it doesn't have to be. Yeah. Usually a sub n is positive, but it doesn't say it has to be positive, so I'll just take that off there. So what we can do is plug in n plus 1 into our expression for a sub n. We did this the other day. So you cross multiply, subtract n from both sides, you get to that result, which is always true, and hence this is true. And so the original alternating series converges. Okay, let's look at another one. So in this case, a sub n is equal to 1 over the natural log of n plus 1. So does the limit of 1 over the natural log of n plus 1 as n goes to infinity equals 0? Yes, because you'll have the natural log of infinity plus 1, which is going to be infinity. So you get 1 over infinity again. And the other requirement is that a sub n plus 1 is always less than a sub n. So let's plug it in, see what we get. 1 over the natural log of n plus 1 plus 1. Is that less than or equal to 1 over the natural log of n plus 1? So that's 1 over the natural log of n plus 2. Is that less than 1 over the natural log of n plus 1? So cross multiply natural log of n plus 1. Is that less than or equal to the natural log of n plus 2? And you could, inequalities, we don't deal with inequalities that much. Even when I teach pre-calculus, I don't really deal with them. This is probably one of the few cases where you have an inequality. And if you if you multiply by a negative number, you have to change the sign on the inequality, the direction of the inequality. And I guess if you took the reciprocal of those, which is what we did, except we switched sides. So if you kept the same sides, you'd have to change the direction of the inequality. But if I'm doing something like multiplying by a constant, then I keep the inequality in the same direction. And if I would do this, if I take e to the natural log of n plus 1, so I'm doing the exponent of both sides. So you'd end up with n plus 1 is greater than or equal to n plus, or less than or equal to n plus 2. And you add and subtract, or you subtract n from both sides, you get 1 is less than or equal to 2, which is always true. So, I mean, you probably could look at that and say, yeah, that's true, right? Or you could look at this, you might even be able to say it's true, because the natural log gets bigger as the argument gets bigger. So if this gets bigger than this, then this fraction is going to be smaller. But I guess most of the time you could use algebra to prove something like this, where one number is always less than the other number. So that's true. So therefore, that also converges. Here again, a sub n is 1 over the square root of n. And if we take the limit as n goes to infinity of 1 over the square root of n, that's still equal to 0. And I guess, let's see. In the past, I think I've just waved my arms and said this is true, but I'm going to try to be more exact here. So if I take a sub n, I put n plus 1 in for it. So again, if I do both sides like this, cross multiply, it's okay. And if I squared both sides, and n is always greater than 1, so if you square something that, well, I guess it doesn't really matter. You can just square both sides. So you'd get, square both sides, you get that. Subtract n from both sides, you get 0 is always less than or equal to 1. So again, that satisfies both requirements, this one and that one. It seems like I'm missing part of that problem. We'll come back and do that on Monday. Let's do one where it doesn't converge. This one here. So if you take the limit of this part of the series, the limit of natural log of n, well, actually it still does work, doesn't it? As far as the limit. If you take n goes to infinity, you'd have to use L'Hopital's rule. So if you use L'Hopital's rule, you'd end up with the limit as n goes to infinity of 1 over n plus 1 divided by 1. And as you let n go to infinity, it would still equal 0. So it doesn't have to be as simple as the previous cases, just as long as it goes to 0. I guess if you had the alternating series with n plus 1 over the natural log of n plus 1, it wouldn't go to 0, and therefore it wouldn't satisfy the first requirement. And the second one is the natural log of n plus 1 plus 1. So we put n plus 1 over n plus 1. I'll put these in parentheses. N plus 1, n plus 1, plus 1. Is that always less than or equal to the natural log of n plus 1 over n plus 1. So that's the natural log of n plus 2 divided by n plus 2, natural log of n plus 1 over n plus 1. And if you ever get stuck and you don't know what to do algebra-wise, you can always just plug in some values of n and just observe it and see whether it happens. So if we cross multiply, I think that's what I did with this one last time, but since I'm in the mode of actually trying to prove it, let's see what happens. So I guess you could make this the exponent. So you'd have natural log of n plus 2 to the n plus 1 power, and then you'd have the natural log of n plus 1 to the n plus 2 power. And then you could do the same thing that we did where you took e to the natural log. So n plus 2 to the n plus 1 has to be greater than n plus 1 to the n plus 2. Now what do I do? Yeah, I don't think this, I'm not sure if this one is obvious. You might just have to try some numbers. I mean, we can try numbers into here, we can try numbers into there, doesn't matter. And it starts at 1. Actually, what I need is 3 columns. Let's do this because that seems to be easier to evaluate. So let's start with 1. So we'll have 3 to the second power. Here we'll have 2 to the third power. So that's 9, and that's 8. Well, that one's we've already shot. That hadn't worked. Let's see. So then you'd have 4 to the third power and 3 to the fourth power. Let's see if I brought my I have my calculator somewhere here. So this is 64. 3 to the fourth power is 81. So then we have 5 to the fourth power and 4 to the fifth power. 625, 4 to the fifth power, 1024. Let's try it again. I don't think it's going to change, but see, this is a case where at some point, only the first term, it doesn't satisfy the requirement. And it doesn't, to me, it wouldn't make that shouldn't be the difference between convergence and divergence. So I'm not sure if I'm ready to say this thing doesn't converge just based on that one term, which is only different by 1. And I didn't bring my solution manual. I don't remember the answer, so we'll look at that next time. We'll come back to that one. That's a question mark. Okay, so there you go. There's the homework for that section. If you have one, don't worry, it won't be that complicated. So if you can pull out your sheet with the different tests criteria on it, because what we're going to do, we're just going to try to figure out if we can figure out which test makes the most sense for these different series. And if it doesn't make sense, there are a couple that we can't do yet until we do the ratio test, so we'll skip over those. So I pretty much finished grading the test yesterday. I also woke up last night and my eye was still hurting even after having been closed for 4 hours. I had to take some aspirin or some ibuprofen or acetaminophen or whatever that stuff's called. Anyway, I haven't put any numbers on them, but I have a general idea of how things went. But I probably won't hand it back till Tuesday. So I'm just going to write these out. First one should be obvious. We've just been talking about it. And I forgot to put infinity at the top. We might actually be able to just answer this based on one of the problems that we've done already today, because it was the other way around, wasn't it? We had the natural log in the numerator and the an n term in the denominator, so it's flipped around. And so in this case, first it's an alternating series, so we'd use the alternating series test. And because the natural log grows at a smaller rate than just n by itself, that's going to go to infinity. So in this case, a sub n will go to infinity. But for right now, we're just going to look at, instead of going through and writing all the verbiage that goes along with it, we're just going to try to identify if we can tell what test we would use. Okay, the second one usually ones involving factorials, you have to use the ratio test. So we haven't talked about the ratio test, so skip over that one. So we'll go to the third one. In any of these, the first thing you should think about is the nth term test. If the nth term does not go to 0, then the series diverges. So the question is, for this one, does the nth term go to 0? So just put you could put some numbers in, see what you get. Or you can think about what's happening is if you look at the natural log, and as you increase n, you're going to actually be going the opposite direction than you think you might. So if you look at the natural log function, it looks something like this. And so as n goes to infinity, 1 over n goes to 0. Therefore, the natural log of 1 over n goes to negative infinity. So you're actually going this way instead. So this one would be the nth term test. But it only applies if the nth term of if it's the natural log of n, then it still wouldn't it'd still be a problem, because then you'd have the natural log of n would get bigger. So both the natural log of n and the natural log of 1 over n both would diverge, because the nth term is going to one's going to go to positive infinity, the other one's going to negative infinity. Okay. The next one, anytime you see something that has directly or has or you can factor it to make it as such, is going to be a telescoping series. So, if I'd actually seen this as n squared plus 3n plus 2, which is the same as what's shown on the paper, but it's easier to see it when it's on the paper, when it's as two factors. We know we can use partial fractions to break that up And one of the coefficients is, I don't know if this is I mean, we saw it a lot when we did partial fractions. Usually one of the coefficients is positive and one is negative. So if you have one that's negative and one that's positive, then you have a telescoping series ultimately. We don't see that immediately here, but I wonder if there's some kind of math law that says that if you take a factored expression like this, if the A is positive and B is negative, or the other way around. I don't know. I don't remember of any that haven't both been positive, but I could be wrong there. Especially if there's just a constant in the numerator. So just write down telescoping series for right now. We'll come back and figure out what the value is. But for right now, we're just identifying the different kinds. Okay, what's the next one look like? So anybody have any thoughts on that one? Again, if you do the nth term test, it goes to 0. So we can't immediately say it diverges. So it has a chance. It's not really it's not a geometric series. It's not a telescoping series. It's not an alternating series. It's not a p-series exactly, but I could kind of see it being a p-series if I simplified it. So a lot of times if you think about, can I take that expression? Oh, and that reminds me of the problem we did the other day, so I'm glad we got to this one. Anyway, you could either use the ratio test or the, not the ratio, what is it called? It's called the limit comparison test or the direct comparison test, but we'll come back to that since we were talking about that problem from yesterday, and I said, why was it in the section that it was, and we couldn't figure out, or at least I couldn't figure out how to do it. So I looked in the solution manual. I cheated. That's okay. I'm allowed to do that. You guys aren't. Let's see, which one was that? Yeah, it was this one. What we found out was that we took this as the simplified b sub n, and we showed that that converged, but this, what was it? I'm trying to remember exactly why we said that. Oh, it actually diverges. Yeah. So we looked at that and we said it diverges. But this direct comparison test work, as far as the diverging part works, this thing actually had to be less than that. And this thing's greater than that because I'm adding 1 to the denominator. So that term has to be smaller than that. So just because this diverges doesn't mean that diverges. If this converged, then that would converge. But it's the other way around. So what you're supposed to do is actually use a different b sub n. So instead of b sub n being the natural log of n over n, it's b sub n is equal to 1 over n plus 1. And in this case, 1 is going to be less than the natural log of n. Because for n, and that's why they start at 2 instead of at 1. So if you start at 2, the natural log of 2 is that true? Natural log of 3 would be, did it start from 2 or 3? Maybe it started from 3. Anyway, I looked in the manual, and this is what they did. So there's two ways of changing the original expression. Is by replacing the natural log of n with 1 or n plus 1 with n. And in this case, it turns out this one is less than that one. B sub n is less than A sub n. And if you look at this, this ends up diverging. And it diverges because, well, actually, you could use the limit comparison test again. You know, if you take 1 over n, 1 over n is, you know, why can we say that's, why did they say that? I forgot what test they used to say that diverges. But this one does diverge, and this one's less than that. So if the smaller thing diverges, then the bigger thing diverges. So it was just my selection of how to simplify the whole thing that was my error. Okay, back to our question here. So what you could do is, if you multiplied this thing out, you'd have 1 over n squared plus 3n. And so a sub n would be equal to 1 over n squared plus 3n. And b sub n would be equal to 1 over n squared. Again, we're gonna work, or you're gonna work through the whole thing. Today we're just thinking about how we would get started. So what we would do is we would look at the convergence of this, which is a p-series, and this would converge because it's a p-series, and because this is always greater than that. If this converges, then that converges. Okay, that's the whole idea there. So just write down direct comparison, and okay, let's look at the next one. One over n to the 1.04. Okay, so Jacob, what kind of series is that? P-series. And what's the convergence criteria for a P-series? So if P is greater than 1, it converges. Yeah, so that one's pretty simple. That's just you just have to recognize it as a P-series. So go ahead and write that down. For all of these, I'm going to have you write out the justification. You know, at this point we've just said it's a P-series, but what you'll ultimately write is this is a P-series, and the convergence criteria for a P-series is such that if P is greater than 1, the series converges, hence this series converges, something along those lines. Okay, what do we got next here? So obviously it's not a simple test, a simple series. So that usually means you can use probably the direct comparison test or the limit comparison test. And usually if you have some question about whether the if you look at it, what could you simplify it down to? 1 over n, probably. But the direct comparison test would probably be a little bit harder to prove. So I might use the limit comparison test instead. you have to deal with ratios of stuff, but as long as you can prove that the limit goes to some value when you substitute n plus 1 in for n. And in both cases, the plus 1 is going to end up being insignificant. So it looks to me like if you look at the ratio, if I let a sub n be equal to 1 over n squared to the natural log of n, and I let a sub n, b sub n equal 1 over n, I think we could make some kind of conclusion about this ratio. Actually, we don't have to put n plus 1 in there. We just have to take the ratio of these two. It doesn't look like that difficult an expression to evaluate. As long as the limit goes to, well, actually it doesn't, does it? If you take the limit of a sub n over b sub n as n goes to infinity, that's going to be equal to 1 over n square root of the natural log of n divided by 1 over n. So these cancel out. Well, actually, it does go to 0. Yeah, actually, it goes to 0, which is still fine. You'd end up with 1 over the square root of the natural log of n, and that equals 0, which is fine. It's not 1. In the past, we've had a lot of cases where this thing ends up being 1, but in this case, it ends up being 0, which is still fine. It doesn't have to be some non-zero number. So it looks like, let's write that down. So that looks like a good choice to try that. So that's called the limit comparison test. Okay. Next one. Now, if the n wasn't there in the front, that would be a geometric series. And we'd be able to say that that converges because and you might think it's going to be maybe the direct comparison test if you just drop the n. Except I think that only works if it diverges. This is actually, we'd find out that it's a ratio. The ratio test works best. Usually if you've got complicated expressions where you're multiplying stuff together and things are raised to powers or factorials, the ratio test, which we haven't talked about yet, makes the most sense. Okay, so we're gonna stop on that for right now. We're gonna talk about the ratio test, so we can work some of those things. So yeah, these are our last two tests. They're called the ratio test and the roots test. If you look at, just as an example, if you look at, I told you to put it away, but if you go to page number 1, 2, 3, the top of page 3, it's n over 2n plus 1 raised to the n power. So if you have a quantity, some quantity raised to some n power, that's the root test. Ultimately, what that means is when you have a quantity taken to some n power, one big quantity, all you have to do is you basically remove the n, the power, and you see whether if the term inside the parentheses goes to 0 or is less, pardon me, if it's between 0 and 1, then it'll converge. If this thing in the parentheses is greater than 1, then it diverges. It's pretty simple. The root test, it's not used that often. And it comes down to the fact that if you take any number that is less than 1 and you raise it to an infinite power, it goes to 0. Whereas if it's greater than 1, then it goes to infinity. But anyway, we'll talk about the root test in a second. So the ratio test here. So the ratio test says let a sub n be a series with non-zero terms. A sub n converges absolutely if the limit as n goes to infinity of the absolute value of a sub n over a sub n plus 1 is less than 1. The series diverges if the limit as n goes to infinity of the ratio of a sub n plus 1 over a sub n is greater than 1, and if it's equal to 0, we can't conclude anything using the ratio test. Yeah, so if this ratio a sub n plus 1 over a sub n is greater than 1, including infinity, then it diverges. If it equals 1, we have to use another test. And this is the test that is used to determine ultimately to determine the values of x that an infinite series, useful infinite series, are valid for. And then the endpoints are evaluated if there are endpoints to the interval. They're evaluated using one of the other tests. For this case, we're not using it yet for that purpose, but I'm just giving you previews of coming attractions as far as just pointing out this is an important test. It's also a test that is used, as I said, for things like factorials or where you have things raised to a power multiplied by more complicated functions. It's the most useful one, I guess. So here we go. So we have 3 to the n over n factorial. Summation from n equals 0 to infinity. So a sub n is just the term in the infinite series. So a sub n is 3 to the n divided by n factorial. A sub n plus 1, all you do is replace n with n plus 1. Like that. So we take the limit as n goes to infinity of the absolute value of 3 to the n plus 1 divided by n plus 1 factorial divided by 3 to the n divided by n factorial. And the absolute value comes into play if you have, well, it'll come into play later. It involves, if you have an alternating series, the alternating part kind of gets wiped out because you take the absolute value, so everything becomes positive, so you can get rid of that term ultimately. Okay. So the easiest thing to do is to take the reciprocal of the denominator and multiply it. So changes division problem into a multiplication problem, somewhat multiplication problem. So we have the numerator 3 to the n plus 1 divided by n plus 1 factorial, and we multiply by the reciprocal n factorial over 3 to the n. And then you can just rearrange things. So we'll get 3 to the n plus 1 over 3 to the n times n factorial over n plus 1 factorial. And this happens all the time. Okay, so you start with your original complicated fraction, a sub n plus 1 over a sub n. Take the reciprocal of the denominator, and then rearrange the terms so that the like terms are in a single fraction. And then use the properties of exponents here. So 3 to the n plus 1 over 3 to the n is just 3. 3 to the first power. And the second one, n factorial over n plus 1 factorial, is 1 over n plus 1. Why is that? Because n plus 1 factorial is n plus 1 times n factorial. Remember, n plus 1 factorial is equal to n plus 1 times n factorial. So this, when I write this as that, the n factorials cancel out, and I'm just left with n plus 1. And so if you let the limit as n goes to infinity, you get 0 for this particular case. So the convergence criteria says that if the limit is less than 1, which 0 is less than 1, then the original series converges. So we'll write that out. We'll say according to the convergence criteria of the ratio test, since the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals 0, which is less than 1, the series converges. If you had n factorial over 3 to the n, it would diverge because you take the limit and everything would be flipped over, and you'd have n plus 1 over 3, which would be infinity. Okay. Okay, so here's another one. Again, without the n in the numerator, it would be a p-series, but it's a little more complicated than a p-series. So a sub n is going to be n over 2 to the n. A sub n plus 1 is equal to n plus 1 over 2 to the n plus 1. We take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which is the limit as n goes to infinity of n plus 1 over 2 to the n plus 1 divided by n over 2 to the n. Take the reciprocal of the denominator of the big fraction, like that. Rearrange the terms. 2 to the n over n plus 1, n plus 1 over n. Simplify. So we'll get 1 over 2 times n plus 1 over n. Can't simplify that. But you can see that as n goes to infinity, this term is going to go to 1. So this is going to stay at a half because it doesn't involve n. This term involves n, but it will go to 1. And so you'll get a half times 1, which is a half, which is less than 1. So that series will also converge according to the ratio test. Let me show you I don't think I've ever done this before, but if you did the series, the summation from n equals 1 to infinity of 1 over n, we know that already diverges because of the p-series test. But let's apply the ratio test to this and see what we get. So you get a sub n is 1 over n, b sub n is 1 over n plus 1. So you take the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n, absolute value, which is the same as the limit as n goes to infinity of 1 over n plus 1 times n over 1, which is n over n plus 1, which equals 1. So if you try to use, you can't always use the ratio test because there are certain cases where the answer will be inconclusive. If you had 1 over n squared, we know that converges because it's a p-series with p greater than 1. But if we use the ratio test for that, we'd end up with the same kind of situation. The limit would end up being 1, and therefore we can't conclude anything from the ratio test. So it's not flawless, especially when it comes to simpler series like that. So that's an example of being inconclusive. So we'll write that down. So this test is inconclusive for and I'm just going to present the root test. So it says that if you have actually it's a root test. I was doing the exponential test, but so that example I gave was wrong earlier now that I think about it. But if you have some series a sub n, which is to the nth root instead of the nth power, this series, the original series that involves the root. Well, actually, the original series doesn't involve the root. Yeah, actually, you do use the root test for this. Sorry. So if the original series is raised to some power, what you do is you take that original series and you take the nth root of that power to the nth power. When you take the nth root of something to the nth power, you basically take away the parentheses. You take away the exponent, and all you're left with is the term inside the power. So if by removing the exponent that's applied to the entire series a sub n by taking the nth root, if you take the limit of that term, if it's less than 1, it converges. If it's greater than 1, it diverges. And probably if it's 0, if it's 1, it's inconclusive, just like the last test. And then you have to use a different test. Okay, so yeah, there's the same 3 options. So if you look at, if you look at that problem on the top of page 3, you'll see that it's n over 2n plus 1 to the nth power. And if you take the nth root of that, all you're left with is n over 2n plus 1. And if you take the limit of that as n goes to infinity, you'll get a half because you get n over 2n. The plus 1 term becomes insignificant. So that means this one ends up being converging because of that. But we'll look at it again next time if you don't have your paper out. So that's all. Those are all the tests. I won't assign this homework till next time. But now we have all the tests we need, and we'll be able to answer all the things on our paper. So work on that, finishing that probably most of all of next period, as long as we don't have snow.